James Prescott Joule studied the relationship between mechanical work and heat. He used an apparatus like the one on the left, and because of his work, we named the unit for energy, the joule, after him. Here we see a mass that will be dropped. Annotate that for you. So here we see a mass. So the mass is going to be dropped. As the mass drops, it's going to, of course, lose potential energy, and it's going to pull this string, and the string is going to rotate the cylinder. When the cylinder rotates, the paddle wheel, which is also attached to it, will rotate. Now, the paddle wheel is immersed in water. So in order to turn, it's going to do work on the water. As the paddle wheel does work on the water is going to increase in temperature, and Mr. Joule is going to use this thermometer to measure that change in temperature. Therefore, he's going to relate the mechanical work of the falling mass to heat, the increase in temperature of the water. And this has led to all kinds of understandings about heat. Remember, heat is a transfer of energy. Heat is not the same as temperature. Heat is the transfer of energy, the transfer of thermal energy, and work, and other forms of energy. So here we see an example. A Joule's apparatus drops a 15 kilogram hanging mass, 65 centimeters, which causes a stirrer to spin in a sealed chamber filled with 250 milliliters of water. Okay. And we're going to assume that no energy is lost to the environment. It's all contained inside that chamber. And we want to determine the temperature change of the water. We were told that the specific heat of water is 4,186 joules per kilogram degree Celsius. And that is actually a known value that's given on your equation sheet. So let's write what we're given here in this problem. We're given that the mass of the hanging mass, I'm going to call that M of M. The mass of the mass is equal to 15.0 kilograms. We know that the height, or the distance that it falls, is equal to 0.65 meters. Remember, we want to use kilograms and meters because we're going to be doing calculations here. Causes a stirrer to spin in a sealed chamber filled with 250 milliliters of water. So we're going to say the mass of the water. Well, 1 milliliter of water has a mass of 1 gram. So 250 milliliters is 250 grams, or 0.250 kilograms. And we are also given this constant. The constant is the specific heat of water. That's 4,186 joules per kilogram degree Celsius. And we are given, well, we know the constant G. G is the acceleration due to gravity near Earth's surface. It is 9.8 meters per second squared. All right, so let's solve this problem. We want to find the change in temperature. We want to find delta T. So we start with this equality. We know that the change in potential energy, is going to be equal to mgh. And the amount that the potential energy changes is going to be equal to the heat that is transferred to the water. The equation for heat is represented by, so let's write that up here. Heat is represented by capital Q. And the equation for that is mc delta T. Okay, that shows that the amount of heat energy that's added to a material is going to increase its temperature by a certain amount based on both its mass and its specific heat capacity. So we can say mgh equals mc delta T. And this is the mass of the water. This is the mass of the mass. Okay, so let's solve this equation as we do for delta T. Let's divide both sides by m and by c. We're going to end up with delta T. We use a capital T usually for temperature because we tend to use a lowercase t for time. So we say that delta T is equal to mgh over mc. And often you'll see C, the specific heat capacity, is written as C sub P. In fact, that's a more standard way of writing it. So why don't I write it that way? C sub P. Okay, now we can substitute in our values. Delta T is equal to the mass of the mass, mass of the water. Okay, the mass of the mass is 15 kilograms, 15.0 kilograms, times G, times 9.8 meters per second squared, times H, and the height that the mass fell was 0.65 meters, divided by the mass of the water, which is 0.250 kilograms, times the specific heat capacity of water, 4,186 joules per kilogram degree Celsius. Okay, and as usual, we're going to want to cancel anything that cancels out of this equation, but there's a little bit of a twist. Okay, the twist is this. We have a unit here that's new to us, joules. Well, it's not brand new to us, but we need to figure out how that cancels with all these meters and seconds and kilograms. Well, let's do this first. Let's cancel kilograms. We know that this kilogram is going to cancel with this kilogram. Okay, that's pretty easy. So then what are we left with on the top, on the numerator of this equation? We're left with kilograms times meters, divided by seconds squared. Kilograms meters squared per second squared. Well, I've got good news for you. The unit of 1 joule is equal to 1 kilogram meter squared. That's not a kilogram, that's a kilogram. 1 kilogram meter squared per second squared. Okay, so what did we have on the bottom here? We had kilograms, meters times meters, kilograms meters squared per second squared. And then on the bottom, we have a J, joules, and that's the same as kilograms meters squared per second squared. So this unit, joules, cancels all these other units that are in the numerator. And what we're going to be left with is degrees Celsius. It's in the denominator of a denominator, so it's going to end up being in the numerator of the answer. So delta T is going to be equal to 0.091 degrees Celsius. Why is 0.091? Well, you might, so even in the example in your book, it says 0.0913, that book. But in our given, We only had two significant figures here. We only had two significant figures here. And so we can only have two significant figures in our answer. So we end up with 0.091 degrees Celsius, or in scientific notation, we would say 9.1 times 10 to the negative second degrees Celsius.